Hello everyone, my name is Vipin Abram and in today's video we'll be talking about capacitors when they are connected in series and parallel combinations, right? So without wasting any more time, let's get started. Okay, the first topic that we'll be discussing is when capacitors are connected in series, right? So you guys can see it in the diagram. So I have three capacitors. First capacitor having capacitance C1, second capacitor having capacitance C2, third capacitor having capacitance C3, right? And they are connected with a battery source having a potential of V. Is that a yes or no? Right. Okay, now this kind of arrangement is what I call as a series combination, where one capacitor is arranged one after another, right? Just like a series, right? So this kind of arrangement is what I call as my series arrangement, right? Or series combination, right? Now again, why I'm saying that it's a series combination, one of the good answer to the question is because there is no junction involved. Now why I'm saying junction, now what is junction first of all, right? Junction is a point where your charges or your currents divide, right? So let's say at a point I have, let's say some charge Q was coming, so at your a point charge Q will be divided into two parts, Q1 and Q2, right? So if your charges or your current, right, in the in the coming next chapter we'll talk about current also, right? So here if the charge is dividing, then this kind of connection is what you call as a parallel connection, right? If the charges are not dividing, right, they're going one after another, then we say that combination is a series one, right? Okay, so you guys can see it in the diagram that if some Q charge is provided, then that Q charge will not be divided anywhere. Can you guys see? Because there is no junction in between, right? So that's why this is a series combination, right? I hope you guys can understand, right? Great. Now one more important thing you have to understand, that whenever we talk about a capacitor, right, the charge that is on your positive plate is the charge on your capacitor, but in real sense the overall charge on a capacitor is actually zero. Is that a yes or no? Right? And you have to remember the law of conservation of charge. Now what is the law of conservation of charge? That is, in an isolated system the net charge will always be equal to zero, right? All charges can neither be created nor be destroyed. Is that a yes or no? So basically this is an isolated system. I hope you guys can understand, and you guys can see right now when there is no charge, the final value of the charge is actually coming out to be zero, right? Very similarly, this is also an isolated system, right? Can you guys see that? This plate and this plate, this is also an isolated system, and right now it is also neutral. There is no charge there. Very similarly, this is also an isolated system. Very similar, this is also an isolated system, right? And very similarly, this will also be an isolated system. So you have to understand, right now I am not providing any charge, right? Just assume that this connection is off, right? So when it is not charged, isolated system, there is the net charge is coming out to be zero, right? So after charging also the net charge should be zero, right? So let's say the connection is complete, let's say the charge is coming, let's say some Q charge is providing, so Q charge is providing, Q charge will come to your first capacitor, right? It will charge your first plate with plus Q charge. I hope you guys can understand very nicely. The next plate will be negatively charged. I hope you guys can understand. Again, you guys can see making the net charge on your capacitor to be zero, plus and minus, as I say, is an isolated system, right? And inside that the net charge should be equal to zero. Very similarly, let's talk about this now, right? Again, like I said, it is an isolated system, right? So if it is negative here, then this particular plate should be positively charged, because like I said, isolated system, the net charge should be equal to zero. I hope you guys can understand, right? The net charge before and after should remain same, right? I hope you guys can understand. So if that is true, then this plate will be positively charged. If that plate is positively charged, then the next plate will be negatively charged, making this neutral, right? I hope you guys can understand, right? So if that is true, what about this system, right? Again, isolated system. So what is going to happen? This will be positively charged, it will be inside, not outside, plus, and obviously correspondingly negative to the other plate. I hope you guys can understand, right? Now the important conclusion from here is that in series combination, whatever charge that you're giving to the capacitor, right, no matter how many series combinations of capacitors are there, right, all of them will have equal charge, right? All of them will get equal amount of charge at the same time, right? I hope you guys can understand, right? So your C1 capacitor will also get Q charge, your C2 capacitor will also get Q charge, and your C3 capacitor will also get Q charge, and they will be charged, but they will be charged by the similar charges, right? I hope you guys can understand that, right? Okay, now let's say, now you guys can see your C1 capacitor is being charged with Q charge. So the moment it is charged, the potential difference between the plates of the capacitor has, let's say, some potential V1, right? Similarly for your C2, it will have some potential difference V2, and for C3 it will have some potential difference between the plate as your V3. Is that a yes or no? Now one important thing you have to understand, that whatever potential is there, that is provided because of the potential difference that is providing by the battery, right? So can I say the net potential V can be written as V1 plus V2 plus V3? I hope you guys can understand, right? Okay, so before I do that, I have to write it here. First point, I have to write it in series combination. In series combination, charges on each capacitor will be same. That is the first point which you have to understand, right? But the potential difference between the plates will be different. I hope you guys can understand that. Yes, right? You guys can see it here. Potential difference is different, right? But charges on all the three are same. Q, Q, Q. Is that a yes or no? But I can very nicely write it here that my net potential, that is something which you guys can see here. This is the potential across the terminal, that is V, right? And that V is divided into V1, then V2, then V3, right? So I can write it V is equals to V1 plus V2 plus V3. Is that a yes or no? I hope you guys can understand, right? So I can simply write V is equals to V1 plus V2 plus V3, where V1 is the potential across your first capacitor, V2 is the potential across your second capacitor, and V3 is the potential across your third capacitor. Is that a yes or no? Okay, now one basic relation we all know, C is given as Q upon V. Right, this basic relation we already know, and I can write my V to be equal to Q upon C. I hope you guys can remember this relation, right? So I can write it further. V is equals to V1 can be written as, well, let's talk about your first capacitor. So V1 can be written as how much charge I have given, Q charge, and because of that Q charge, what happened to the potential across your plates? V1, right? So can I write my V1 as, you have to write it Q charge, and I provided it Q charge, right? And obviously its capacitance is actually C1, right? So I can write it Q upon C1. Is that a yes or no? Very similarly, I can write, this is again Q charge given capacitance is C2. Very similarly, Q charge is given capacitance is C3. Is that a yes or no? So this is my one equation, right? This is equation number 1, or you can make it, you can write it further as take Q common. This is 1 upon C1 plus 1 upon C2 plus 1 upon C3. You can write it like that also, right? I hope you guys can remember. Instead of this, you can write it equation number 1. Is that a yes or no? Right? Great. Now let's assume, now this is the next important part, let's assume there is an equivalent capacitor which is having capacitance C equivalent, and it is connected to the same battery source, right? Okay, now I will assume that I have one big capacitor, right? Now that capacitor has a value of that of the combination of all the three capacitors. I hope you guys can understand. And again, that capacitor is connected with the same battery source, and the same charge is, is being given so that the capacitor can charge, right? I have assumed an equivalent capacitor which is having capacitance C equivalent, and it is connected to the same battery source. So basically, this is my C equivalent capacitor. Again, same battery source connected and same charge is given, right? So if that is true, so for this one I can write, my V will be equal to, yes, V will be equal to what charge? Obviously Q charge is provided here, what charge I'm providing it, right? Q charge divided by what is the capacitance of your equivalent capacitor, C equivalent. Is that a yes or no? So same potential, same potential battery is connected here also. This is my equation number 2. All I'm going to do is compare my equation number 1 and equation number 2, right? So comparing equation number 1 and equation number 2, and by comparing you will see all your left hand side of these two equations are same, right? So left hand side of these two equations are same. That means I can write it further. Q upon C equivalent will be equal to, yes, Q upon 1 C1 plus 1 upon C2 plus 1 upon C3. Is that a yes or no? I hope you guys can understand. This Q and Q will be cancelled out, and you'll be left with 1 upon C equivalent will be equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3, right? So this is the required expression, right? So whenever you have 3 capacitors which are connected in series and you're supposed to find out the equivalent capacitance, then we can use this formula: 1 upon C1 plus 1 upon C2 plus 1 upon C3 is equal to 1 upon C equivalent, right? And it can be used for n number of capacitors. So I have just proved it for 3 capacitors. You can prove it for n number of capacitors, right? So if let's say that there are n number of capacitors, the equivalent capacitance will be 1 upon C1 plus 1 upon C2 plus ... 1 upon Cn, right? This is the only difference that will happen, right? So let me call this equation number 3, right? So what I will do here is I will multiply equation number 3 by Q square by 2, right? I will multiply equation number 3 by Q square by 2 on both sides, right? So I will multiply it by Q square by 2 on both sides, right? So when I multiply it, what I will get Q square by 2 C equivalent is equals to Q square by 2 C1 plus Q square by 2 C2 plus Q square by 2 C3. So can you guys see here, Q square by 2C was the potential energy. Q square by 2C was the potential energy of your system, potential energy that is stored inside your capacitor, right? So this is the equivalent potential energy that is stored inside your equivalent capacitor, and that is equal to potential energy that is stored inside your first capacitor plus potential energy that is stored inside your second capacitor plus potential energy that is stored inside your third capacitor. Can you guys understand? So one important thing that you guys can understand from here is, if somebody asks you that you have 3 capacitors like these, right, which are connected in series, then what will be the equivalent potential energy that is stored inside these 3 capacitors? The answer is your potential energy that is stored inside your first one plus potential energy stored inside your second one plus potential energy that is stored inside your third one will be the value of equivalent potential energy that will be stored inside all the 3 capacitors. I hope you guys can understand. Is that a yes or no? Great. So if that is understandable, let's try to solve some problems so that you guys can understand much better. So yes, I have find the equivalent capacitance. Okay, so I have this A. Okay, I have to find out equivalent capacitance. 3 capacitors are there, 2 microfarad, 3 microfarad and 4 microfarads are the capacitance here, right? So I have to find out the equivalent capacitance. The first thing is, obviously I have to connect it with the battery source, right? Connect it with the battery source, right? So after connecting it, what is going to happen? It will be charged, right? And I can simply say the equivalent capacitance will be 1 upon C equivalent will be equal to 1 upon C1 plus 1 upon C2 plus 1 upon C3, which we just derived, right? So 1 upon C equivalent will be equal to, yes, 1 upon 2 plus 1 upon 3 plus 1 upon 4, right? Microfarad is already there, so I'm just omitting the units here. 1 upon C equivalent will be equals to, take the LCM, this will be 4 into 2 into 3. I'm just multiplying all of them, right? Okay, so this is 4 into 3 plus 2 into 4 plus 2 into 3. I hope you guys can understand. This is 4 to the 12 plus 4 to the 8 plus 3 to the 6. This 4 to the 8, 16, 24. Right, so 12 plus 8, 12 plus 8, 20, and this is 26. 26 by 24 is 1 upon C equivalent, or I can say C equivalent is equals to 24 upon 26 microfarad. You can solve it further. 12, this is 13. 12 by 13, C equivalent will be, so for this C equivalent is coming out to be, C equivalent is coming out to be 12 by 13 microfarad. I hope you guys can understand. Is that a yes or no? Right. Okay, now let's talk about this one. Second question. I have 1 microfarad and all of them actually are connected in series. Now how you can say that they're connected in series? You can basically first of all connect it with a battery source. So when I connect it with a battery source, then you guys can see the charges will be flowing in series, right? Q, there is no, there is no junction here, right? All the charge will be in series, right? There is no junction here. I hope you guys can understand, right? So all of them are in series, right? So I have all of the value, all of them has the value of 1 microfarad. And how many capacitors are there? You guys can count it. 1, 2, 3, 4, 5, 6, 7, 8. 8 capacitors are there in series, right? Okay, great. So 8 capacitors are there in series, so I can simply write it here. 1 upon C equivalent will be equal to 1 upon C plus 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 1 upon C. This is 1, 2, 3, 4, 5, 6 plus 1 upon C plus 1 upon C. So I'm writing 1 upon C because all of them are having the same value, right? So I can take the LCM of all of them as C. I hope you guys can understand that. Is that a yes or no? Right? So simply this is 1, 2, 3, 4, 5, 6, 7, 8. So 8 will be there, and this is 1 upon C equivalent, and you guys can see C equivalent having the value of C upon 8. I hope you guys can understand, right? So let's say if there was n number of, let's say there were n number of these kind of system which is having this kind of capacitor which is having the same value, then it should be n, and here it should have been C upon n, right? So direct you can also find out this, find out the value directly, C upon n. So the value of C is 1, so the answer is 1 upon 8 microfarad, right? I hope you guys can understand that. Is that a yes or no? Great, right? Okay, so if that is understandable, let's move to our second topic, that is when your capacitors are connected in parallel, right? Now when your capacitor is connected, so you guys can see these kind of arrangement is when I say that my capacitor is connected in parallel, right? So you have to understand here, I can very nicely see I have 2 junctions here, 1, 2. Can you guys see? I have junctions here, right? Now why I'm saying junctions here, because obviously if a Q charge is drawn, right? So the charge will go and it will divide into 3 parts, Q1, Q2 and Q3. I hope you guys can. So your charges are dividing, that means they are connected in parallel. Is that a yes or no? So Q1 charge will be here, Q2 charge will be here, and Q3 charge will be here. And what will happen at your this point, B point, all of these charges, this is Q1, this is Q2, this is Q3, they will come back as your Q. I hope you guys can understand, right? So Q1 charge will charge your C1 capacitor with plus Q1 here and minus Q1 here. This Q2 charge will charge your second capacitor with plus Q2 on your first plate and minus Q2 on your second plate. Very similarly, Q3 charge will charge your third capacitor first plate with plus Q3 and the second place with minus Q3. I hope you guys can understand. Is that a yes or no? Now charges are different here, right? The first capacitor will be charged with Q1, The second capacitor will be charged with Q2 and the third capacitor will be charged with Q3. Now important thing that you have to understand here is this time the potential is same, right? Same potential is applied across your first capacitor, across your second one and across your third one. Same potential differences between your plates. I hope you guys can understand that. Is that a yes or no? So in parallel combination, I can write it here. So for parallel combination, I can simply write it. I can write it the potential difference between the plates between the three capacitors will remain between the three capacitors will remain same, and that is something which we know, right? V potential and V potential. But important thing, this time charges will be different for different capacitors. I hope you guys can understand, right? This time charges are different, right? Okay, great. So potential is same, charges are different, right? So I can very nicely see it here that my Q charge can be written as Q1 plus Q2 plus Q3. Is that a yes or no? Can I write my Q charge will be equal to Q1 plus Q2 plus Q3? Is that a yes or no? Okay, so I will start with that. My Q charge can be divided into Q1 plus Q2 plus Q3. Again, I know my basic definition, that is C can be written as Q upon V, or I can write my Q to be equal to CV, right? Remember this part, right? Okay, now I know my Q can be written as Q1 plus Q2 plus Q3, right? Now let's talk about Q1 here. Can I write my Q1 equal to C1 times V, right? What about my Q2? Can I write my Q2 is equals to C2 times V? And can I write my Q3 is equals to C3 times of V? I hope you guys can understand, right? So I'm just using this formula for whatever capacitance we are talking about, right? So for Q1, I can write it C1 times of V, because potential in all the three cases are same this time, right? Plus, yes, this is C2 times of V, plus this is C3 times of V. I hope you guys can. So your Q can be written as C1 times of V plus C2 times of V plus C3 times of V, or can I write it here Q is equals to, can I take my V common, and this is C1 plus C2 plus C3. I hope you guys can understand. This is my equation number 1 for this particular situation, right? Okay, again I will use the same analogy. I will assume that I have a equivalent capacitor which has a capacitance Cp as the equivalent capacitor, and it is connected with the same battery source, right? So I have a capacitor which is equal to your Cp, which is like equivalent capacitance of all of these, right? Again, they are connected with the same battery source and the same charge is drawn from the battery source, right? Okay, so here you guys can see it in the diagram. So here is my equivalent capacitor, right? So the charge Q is given, right? Because of this Q charge, this is positively charged plus Q, and this is negatively charged minus Q, right? So I can write it very nicely here. Cp is equals to Q upon V. So V is the potential difference here, or I can write it Cp is multiplied by V is actually equals to Q. Is that yes or no, right? I hope you guys can answer. So this is my equation number 2 for this situation, right? So what I will do the same thing which I did it in the previous case, right? I am going to compare, right? I'm going to compare first equation with your second equation. You guys can see here my Q is similar to this Q. So when I compare it, I will simply get, I can write it here. I will get Cp times of V is equals to C common, sorry, is equal to V common. You guys can see here, yeah, V common C1 plus C2 plus C3. Is that a yes or no? Right? So your V and V will cancel out, so you will get your equivalent capacitance in the case of your parallel combination coming out to be C1 plus C2 plus C3. Is that understandable? This is equation number 3. Is that understandable? Yes or no? So whenever you have a parallel combination, if you want an equivalent capacitance, all you have to do is just simply add all of the capacitances, right? Okay, now one more interesting thing is, so what I'm going to do here is, I know my potential is constant this time, right? So I will multiply, we'll talk about potential energy here, right? So multiply equation 3 by half V square on both sides. So on both sides of your equation number 3, I'm going to multiply it with half V square. This is half Cp V square is equals to half C1 V square plus half C2 V square plus half C3 V square. C3 V square, right? I hope you guys can understand. And can you guys see that this is potential energy? This is equivalent potential energy for your equivalent capacitor. This is the potential energy for your potential energy that is stored inside your first capacitor. This is the potential energy that is stored inside your second capacitor. This is the potential energy that is stored inside your third capacitor. Can you guys understand that? So can I write it? U equivalent is actually coming out to be U1, that is the potential that is stored inside your first one, plus U2 plus U3. Same relation I'm getting, equation number 4. Same relation. So in the case of a series or in the case of your parallel combination, the equivalent potential energy that is stored inside is simply the algebraic sum of all the individual potential energies of your capacitor, right? So for example, if let's say some 10 joule is the potential energy stored inside, and let's say 20 joule is potential energy stored inside your second one, and the 30 joule is potential energy stored inside your third one, then the net potential energy will be 10 plus 20 plus 30, right? This is 60. Can you guys see that? 60 joule will be the answer, right? It is simply individually add all the potential energy, whether be it in your series combination, whether be it in your parallel combination. I hope you guys can understand that, right? Okay, so if that is understandable, let's try to do some questions so that we can understand. So here you guys can see it's simple one. So I have 1 microfarad, 2 microfarad, 3 microfarad connected with a battery of V, right? Find the equivalent capacitance. Very simple. The answer is yes. C equivalent is equals to C1 plus C2 plus C3. Is that a yes or no? So this is simply equals to 1 plus 2 plus 3. Yes, 6 microfarad, right? Very simple. I hope you guys can answer, right? Okay, next question. Now this is a question which came in 2019 mains. Okay, let's try this. In the circuit shown, find C. Okay, here is the circuit. Find C if the effective capacitance of the whole circuit is to be 0.5 microfarad. Okay, all the values in the circuit are in microfarad, right? So all of the values are in microfarad, right? Okay, great. So here is my A and here is my B. Obviously I will connect it with a battery source, right? I will connect it with a battery source here, right? I'm supposed to find out the value of this C, and I'm given the equivalent capacitance of this full circuitry is 0.5 microfarad, or I can write it here half microfarad, right? Okay. So when it is connected with a battery source, so can you guys see here some Q charge will be given, and at this point there's a junction. This Q charge will be divided into Q1 and Q2. Yes or no? And can you guys see that that means this whole system and this whole system, they are connected in parallel. Is that a yes or no? So these two systems are connected in parallel, right? I hope you guys can understand that. Is that a yes or no? Right? So these two systems are connected in parallel, right? So I'll just simply redraw them, right? So you guys have to see here, I'm actually going to redraw them, right? Okay, so here is my A point, right? So here is my first capacitance, that is C, right? After that it is in parallel combination, right? So I'll just simply redrawing it. Okay, so you have to understand, when the current is going here, Q1, further this Q1 current is divided into two parts. Can you guys see? Let's say this is Q2 and Q3. Is that yes or no? So at this point again you are getting a parallel combination. Can you guys see this? this and this, they are in parallel combination. I hope you guys can understand that. So accordingly I will, so let me just say this is my point B or C, right? Or D. Okay, this is point D. So here is my point D. So at point D I'm actually dividing my current, right? Dividing my charge, right? So this is something like this here. Okay, I hope you guys can understand this. Yes. Okay, and this is your point B, right? Very similarly, from here I have this one, and you guys can see again at this point E, again charge is getting divided. So Q2 charge is getting divided into Q6 and Q7, let's say, right? So again at my E point, you guys can see at my E point again there is a parallel connection. I hope you guys can understand. This is my E point, right? So at my E point again a parallel connection is there, right? So this is your one and this is your another one, and then it is connected with your B. I hope you guys can understand this. Is that a yes or no? Right? So let me just very quickly label what is the value of a capacitance over here. This is your 2 microfarad, right? Okay. So and this is your 1 microfarad. This is your 2 microfarad. This is your 2 microfarad, right? I'm not writing microfarad. You guys can just simply understand this. Okay, this is your 2 microfarad. This is your 2 microfarad, 2 microfarad. Okay, great. Now you guys can see here. I will solve whichever is possible. So these two are in series combination, right? These two are in series combination. So what is the equivalent for these two? They are in series combination. So you guys can see we have just studied. So we have just studied. If I can go back, we have studied for series combination. Yes. So if you guys can see, if all of your capacitors are same, right? So for series combination the answer comes out to be C upon N, where N is the number of capacitors which have the same capacitance, right? So the C equivalent can be written as C upon N, right? So I can simply do it. I can simply just write it there. Here I have two numbers, so can I say the C equivalent for those two can be written as yes, C upon N, or I can say C is actually 2 and N is also actually 2, so 2 by 2, or I can say 1 microfarad. I hope you guys can understand 1 microfarad, right? So basically this can be simply redrawn as your 1 capacitor with 1 microfarad capacitance, right? Is that a yes or no? So I'll just simply again redraw it very quickly. This is your C, A point. Let me redraw it. This is 1 microfarad, right? And this is again 1 microfarad after the after the series combination, right? And okay, then what is going to happen? Okay, I think I did some mistake. I'll just draw it again. Wait. I'll just redraw it. Just a minute. So this is your first one. This is your C, right? This is your 2 microfarad, right? And then this is your 1 microfarad, and again this is my 1 microfarad, right? Something like this. And from here 2 microfarad, then 2 microfarad. This is 1 microfarad. This is 1 microfarad. This is 2 microfarad, and this is 2 microfarad. I hope you guys can see that. Right, and this is connected to your B, right? This is 2 microfarad, right? And this is C, right? Okay, so you guys can see here these are in parallel and these are in parallel, right? So what is the value here? This is actually 2 microfarad, right? So the parallel with combination, you guys can see this parallel combination will result into 2 microfarad, 1 plus 1, and this parallel combination will result into 4 microfarad. I hope you guys can understand. So I can again redraw this. So I'm again redrawing this. I hope you guys can understand. This is A, this is C, and this is 2, and this is again 2, again 2 after redrawing. This is again 2, and this is 4 actually, right? And then your B connection, right? Okay, now again we are close. So your 2 and 2 are in series, 2 and 4 are in series, right? So for this series combination, again use the same formula. For this series combination, C equivalent will be equal to Yes, C equivalent will be equal to C upon N, right? Or I can write it 2 upon again 2. Is that a yes or no? 2 upon again 2, this is 1 microfarad, right? So the equivalent for this one is again 1 microfarad. I hope you guys can understand, right? Okay, now for this one I have to do actually, right? So for this one, let me do it. 1 upon C equivalent will be equal to 1 upon 2 plus 1 upon 4, and this will be equal to 4 as your LCM. 2 plus 1, this is 3 by 4, or simply I can C equivalent will be equal to 4 by 3 microfarad. Is that a yes or no? So for this you will get 4 by 3 microfarad, right? So if that is true, I can again redraw this, right? I can again redraw this. This is your A, this is your C, right? You will get 1 microfarad here, right? And you will get, okay, let me draw it properly. This is not nice. Wait a minute. So I'll draw it again. This is my A, this is my capacitor, this is my 1 microfarad, this is my 4 by 3 microfarad, and they are in parallel combination, right? Okay, so this is 1 microfarad, this is 4 by 3 microfarad, this is C, right? So now they are in parallel combination. So in parallel combination, we all know they will simply add, right? So I'll simply get again, I will get here one more. This is A, this is C, this is simply I will get 1 plus 4 by 3 microfarad, right? And this is connected to your B. Is that a yes or no? So this will have, this is 3 plus 4 upon 3, or I can say 7 by 3, right? 7 by 3 microfarad, right? So you will have A, this is C, and this is 7 by 3 microfarad, right? And this is correct. So obviously I know the equivalent capacitance here, right? So I can write it here, 1 upon C plus 1 upon 7 by 3, right, is equals to 1 upon C equivalent, right? So I already know the value of C equivalent. 1 upon equivalent has half value, is equals to 1 upon C plus 3 by 7. I hope you guys can understand that. Is that a yes or no? So this will be 2 upon 1 is equals to 1 upon C plus 3 by 7, or I can write it 1 upon C is equals to 2 upon 1 minus 3 upon 7, right? And this will be 7 taken as LCM. This is 2 into 7 minus 3 is equals to 1 upon C. So 14 minus 3, you will get 11 upon 7 to be equal to 1 upon C, or I can say C is equals to 7 upon 11 microfarad. So value of C is coming out to be 7 upon 11 microfarad. So let's see, is it there in the options? Yes, 7 upon 11 microfarad is there in the option. So I hope you understood the video. I know it's a little bit long, but I hope you understood it, right? So if you have any doubt, you can ask me in the comment section, and thanks for sticking around.